solutions pretty quickly. In this video, if you need to, you can go back, you can pause it to try to see what I'm doing to set up these problems. So this first problem was the one where we had two stones dropped from rest from a certain height, one after the other, and there's a whole bunch of questions that follow. But we need to plot the speed versus time for both in the same graph, and then the height or position versus time for both of them in the same graph. So I can set it up a bunch of different ways. I'm gonna make my my data tables for my initial values right here. So my DI for both of them is going to be 0. Okay. Let me just format this a little bit, make everything centered. The VI for both of them is also 0. They both start from rest. The acceleration for both of them is gravity. So this is one way to set it up. I know that I've done it differently in the past, but this is just one way in case I need to change something specific to one of the balls versus the other one. The final position actually is ground level, so I'm actually going to make that 0 because it's falling. So that means I got to go back to D initial, and I got to pick a starting height. So I think when I did this, I started with 94 meters. I'm just going to pick something. I'll do 50 meters. So they're both going to start at 50 meters, and they're both going to fall down to the ground at a rate of negative 9.8 meters per second squared. Okay, so I need a column for time. I need a column for V1, that's V final 1, the final velocity of ball 1, and V final 2. All right, I'm not putting the units in. It's going to be meters per second. So I start with 0 time, excuse me, and I'm going to do 0.5 second intervals. I just want to show you, the basics of what we need to do in these kinds of problems. So I'm copying that formula. Let's do 20 seconds. It's probably plenty. If it's not enough time based on 50 meters, I can fix that later for the distance. Okay. Now the formula for V1 is going to be initial velocity plus acceleration times time. So the initial velocity of ball 1 is this cell right here. So I just want to make sure that it always goes back to that cell, which is why I'm putting a $ in between. Okay, so it's that that cell plus the acceleration times time, which is this cell. Again, put the $ in, so it always goes to that cell, times the time change, which is in this L column, which is this cell. Now, don't put a $ there because you don't want it to only go back to that cell. You want it to repeat the calculation for each time you change cells, okay? All right, so those velocities have been calculated. Now, let's say I have to, it's not given in the problem, so I'm going to come up with a time that the second ball is released. Let's say ball 2 is released let's say 2 seconds after ball 1. Okay? All right, so now I need to start the same kind of calculation I did for ball 1. I have to do the same thing for ball 2, but I need to start it at 2 seconds, right? 2 seconds after, ball 1's already been moving, okay? So this is where I'm going to start my calculation for ball 2. But it's still going to be like the time for ball 2, it hasn't been moving from 0 to 2 seconds, right? It starts moving when the elapsed time is 2. But as far as calculating its velocity, the starting time for it is still 0, which would be cell L2. Okay? So as far as calculating it goes, we're going to be, referencing that cell up there in the formula, but we're just going to be inputting the formula in this cell over here. Okay, so it's going to be the initial velocity of ball 2, which is this cell right here. I'm going to put a $sign in, okay, plus the acceleration of ball 2, which happens to be the same acceleration, times time, which is this cell, L2. Okay. And when we look, we should have the same values as the times change, right? So after 0.5 seconds, ball 1 is moving at negative 4.9. And if we look at this at 2.5, right, that's the time change, ball 2 is moving at negative 4.9. So this is just one way to do it. Now, what was ball 2 doing up to that point? It was at rest. So I need to manually type in 0. Again, this is just one way to do it. There's a few different ways to do it. This might be the most straightforward. I don't know. It kind of depends. Everyone has a little bit different way of doing these kinds of problems. Okay, so there are my velocities. All right. Now, I want a graph. All right. So click the insert chart. And I have a nice line graph, and this does show me what I expected. Okay. They're both accelerating at the same rate. So a velocity time graph, you're going to have a linear relationship, negative slope. The slope of this would be negative 9.8 meters per second squared. They both have the same slope. And the difference, the space between them just shows me that that's when the second ball was released 2 seconds later. Okay, so this makes sense. Okay, I want to repeat this for position versus time. I'm going to just create a completely new table to do this. I'm going to make some room, so I got to add some columns. Okay. So height 1, height 2. Okay. Let's make everything centered. Okay, the equation for height is d initial plus v initial times time plus 1/2 at squared. Okay, so equals d initial of ball 1 plus v initial of ball 1 times time. I gotta make sure I go put $signs in between, so it always comes back to these cells. Okay, v initial times time, that's this cell, plus 1/2, so I'm going to use 0.5 times the acceleration, which is this value. So I want it to come back to that cell every time. So I use the $sign, times time squared. That's this cell, caret 2 to square it. Okay, there we go. All right. Now I'm going to repeat the same equation right here, the same formula, but I'm going to make sure I reference the J, that cell values instead of the I, and I want to start it at 2 seconds. So a shortcut is if I go to this formula that I'm using here and I go up to the formula bar and I just kind of highlight everything up to the equal sign. Do not highlight the equal sign. Right click, copy the formula, and then I'm going to go into this cell, hit equals, click into the formula bar, and paste. All right. Now, where there's an I want a J. So I'm just changing those, all the I's to J's. Okay. And paste the rest of that out. All right, let's just quickly check. All right, 50 and 50, 48.78, and so on. Okay, so it's doing the right thing. They're both falling the same distance in the same time change. Now, what was H2 doing from 0 time to up to 2 seconds? It was staying at 50 meters. So I'm just going to manually type that in. Okay. There's my data. Now, I don't know if 20 seconds, if it hits the ground or not, but we'll see. I'm going to insert my graph here. Okay. All right, we can see like if there's 0, all right, it's way, it hits the ground pretty quickly. But I can still use this graph. I mean, if I wanted to, I could just look at that part. Actually, let's see. Where does it hit? So it hits somewhere between 5 and 5.5. So why don't I just try deleting this data here and see what happens with my graph. Okay, so I can use this to figure out what, answer the questions, right? So based on this, we can see that this object, right, it falls, it has a curved path because it's accelerating, right? And there's a t squared component to the equation. When I release the second ball, right, I can see that when they hit the ground, the space between them, okay, the distance between them is greater and greater, all right? So that's one of the things. It's not, the distance isn't staying the same, right? So if you kind of look, right over here at just around 2 seconds, there's a certain amount of vertical distance between the two, okay? But then at 3 seconds, there's a greater amount of vertical distance. At 4 seconds, the vertical distance is getting greater and greater. These lines are not parallel, right? So that's going to help me answer one of the questions. All right, as far as the time change between them hitting the ground, right, the time interval, that has to deal with the velocity. So they're both, one's going to hit the ground, and then 2 seconds later, the other one's going to hit the ground, because that's how long I waited, right? So that's, how I can answer all these questions for part 1, right? Will the difference between their speeds increase, decrease, or stay the same? It stays the same. The separation distance definitely increases as time goes on. The time interval between when they hit the ground is going to be equal to the time interval between when I release them. So, this is where I get that information from these graphs. Okay? All right. So let me add a sheet here for this second problem. Okay, the second problem, a red car at a red light turns green, accelerates at the same instant, blue car passes it at 62 kilometers an hour. That needs to get converted. So why don't I do that conversion first? All right, so 62 kilometers an hour, so 62 times, there's 1,000 meters in a kilometer divided by 3,600 seconds in an hour. Okay, so there's my velocity for the car in meters per second. Okay, meters per second. All right, so it's just kind of putting that in there so I have it available when I need it. Okay. All right, so we need to set up a red car and a blue car. Okay, so let's do this. Red car, blue car. Okay, let's just format everything so it's centered. Okay, the initial. Okay, for the red car it's 0, and for the blue car it is 17.22. Okay, next, D initial. Okay, this action or this scenario, they both start at the same point or location. So we're going to call that the origin 0. All right. Acceleration. Okay, so acceleration of the red car once this starts is 2 meters per second squared. So I'm going to put 2 in there. All right. Let's fix the decimal places. So if I highlight both these columns and I go over here, there's a decrease or increase decimal. I'm going to increase it 2 decimal places because it tells me 2.00 meters per second. Okay. The acceleration of the blue car is 0. All right. I think that's all I need for this. All right. So now I want to plot I want to figure out when they cross each other or meet. So that's position. All right, so let me set up my timetable. All right, I'm going to start time at 0, and let's do 0.2 second time changes. Okay, I don't know. I think 40 might end up being enough. We'll see. It's getting to be a long column, so let me do 0.5 second time changes. Let's see how this goes. Okay. So let's see. Let's get rid of the data after 45. And if I need more time data, I can always fix that later, after I see what my plot looks like. All right, let's get that in there. Okay, so let's do the blue car first. Okay, this is position. All right, and then let's do position red car. All right, and I'm just going to do a little extra formatting. I'm going to make all that font blue for the blue car, and I'll make all this font red for the red car. Okay. So position, again, the same equation, d initial plus v initial times time plus 1/2 at squared. All right, equals the initial position of the blue car. Okay, now it happens to be 0 in this particular situation, so I could avoid even using that in the formula, but I'm going to use it because what if I give you a new problem and all of a sudden the position of the blue car is different and maybe the acceleration of the blue car is different. So if you set this up from the beginning the right way with the right formula, you don't have to worry when you go back. You can just change the original parameters and everything will be updated. Okay, so initial position plus initial velocity, and I'm putting the dollar signs in there so it always goes back to those cells, times time plus 1/2 times, you have to put the asterisk in there or it won't know that you want it to multiply, times acceleration of the blue car, again, dollar sign, times time squared. Okay, there is my data for the blue car. All right, I'm going to repeat the same formula, but I'm going to make sure I reference the K values instead of, when you look at the blue, it's referencing L values. Okay, so I can go up here, copy the same formula to save myself a little bit of time, go into this cell, equals, click into the formula bar, right click, paste, and wherever I see an L, I'm going to change that to a K. Okay, so first one's done. This other L over here is now a K, and K, all right? And you can see, let me just do that. Okay, so you can see, like, if I want to see what my, what cells my formula is referencing, when I click into the formula bar, it highlights all the cells that are being used. And I can see it's only using cells for the red car and then time. All right, so that's just another way to check. Okay, there's all my data plotted. Let's highlight it and insert a chart. All right, so okay, insert chart. All right, and okay, we look at this, and wow, so it happens before 20 seconds. So what I'm going to do to make my chart look a little better is I'm going to come down to 20 seconds, and I'm just going to delete all the data after that. All right, I didn't need all that. All right, when I delete it, my graph is updated. It looks a lot better. And I can see, I don't know, this looks like, it looks like about halfway between 15 and 20. So that's like 2.5. So, I mean, just looking at the graph, it looks like it's at 17.5 seconds is when they meet. And it's just below 300. So I don't know, 298, 297. And then I can go into my table here and actually see when they meet, okay? So if I kind of scroll down, I look at the numbers, right? 13 seconds, the blue car's at 224, the red car's at 169. They haven't met yet, all right? So we thought it was somewhere around 17 seconds. So we look here, right? 284 for the blue car, 272 for the red car. Then at 17 seconds, 292 for the blue, 289 for the red, 17.5, 301 for the blue, 306 for the red car. So we were thinking 17.25. So yeah, it happened somewhere between 17 and 17.5, right? So that looks good. And we were thinking maybe it was like 297, 298. So that also looks good, right, for the position, right? So this is, that's that graph done out. Okay, let's do the third one here. Let's bring the problem over. Okay, just reading real quick here. This is the police officer and the motorist, okay? I'm going to need to convert 110 kilometers an hour to meters per second. I'll do that conversion over here. So I can have Excel do this calculation for me. I just put in equals. So I'm going to do 110, okay, times, there's 1,000 meters in a kilometer. So that's going to convert kilometers to meters, divided by, and there's 3,600 seconds in an hour. All right, so there is my velocity of the motorist in meters per second, and I'll do it to 2 decimal places. Okay, so that's meters per second. And I'm just going to highlight it so we can see it when we need it. All right, so what happens here is at starting time 0, the police officer notices that this car is speeding and they need to go, track it down. Now, from that moment, it takes the police officer 1 second to get his car moving, right? Take the radar reading, start the car, and get moving. So there's a 1 second delay. Now, the motorist has been moving at a constant velocity for that 1 second, right? So elapsed time is really relative to the motorist. Okay, the motorist, the elapsed time kind of keeps track of the motorist, right? So the police officer is going to be plus 1 seconds, right? So let's set up our data here. That's our parameters. All right, so let me just get everything centered. Okay, so motorist, police. Okay. DI for both, they both start at position 0, the origin. Okay, VI for the motorist is 30.56. Police officer starts at rest. Okay, acceleration. The motorist does not have any acceleration. The police officer, once the car moves, the police officer accelerates at 2.10 meters per second. Okay. All right, I think that's all we need for this. Let me just double check the initial. Yep. Okay, so same thing. We want to know when do they meet. So this is a position versus time graph. So let's set up my time and 0, do 0.5 second time changes again. Let's go to 40 seconds. Okay, get rid of those last few. Okay, there's my 40 seconds. Let me just format this so that I get, let's do 2 decimal places. All right. Motorist, police. Okay, their positions. I'm going to make the motorist font blue, and we'll make the police officer font red. All right. So it just so happens it's the same kind of equation as I did in the previous problem. So I'm just going to do equals the initial position of the motorist, okay, $, plus the initial velocity of the motorist, make sure I use the $, so it always goes to that cell, times time, this which is this cell, plus 1/2 times the acceleration of the motorist, which happens to be 0. We still want it in there in case I change something on you, times this time squared. Okay. All right. Same equation for the police officer, but instead of using the I cell values, I'm going to be using the J cell values. So I'm just going to go to this first cell for the motorist. Sorry, right here. And I'm going to copy that formula. Don't copy the equal sign. Copy. Go into this police officer cell, hit equals, up here, paste. And where I see an I, I'm going to put a J. Okay. First one taken care of. Second one taken care of. And the last one taken care of. Hit enter. Oh, wait a minute. I started the police officer at 0 time. I need to fix that. So how do I fix that? let's just go to this first cell right here. Let's copy that equation formula that I'm going to use. Okay, copy. And what we can do is we can just delete. And now I need to do this at 1 second. So 1 second's right there. Let's put it in that cell. Okay, and now I'm going to copy and paste it all the way down, and it'll overwrite these other values. So go to the bottom right corner, click, and drag it all the way down to release, and there we go. Now, manually, I'm going to type in 0 for these two values because the police officer was at rest from 0 leading up to 1 second, right? So at 1 second is when he starts. That's why I put the formula in there. Because at 1 second, the police officer actually starts to move. All right, my data is all taken care of. Let's highlight these values so we can insert a chart. Okay, there's my chart, and it looks like somewhere around 31 seconds. I can customize. I'll do a little bit of customization here. Let's customize the horizontal axis. We'll make the minimum 0, but let's make the maximum 32. Let's see what happens. Okay, so it's a little better looking. Okay. And there's my graph for the police officer and the motorist. All right, and this is how I can start using that information to help me answer some of the questions. All right, I hope this video is helpful.